Hi guys, welcome to the video for the summary of chemical bonding. First, we're going to talk about the difference between intramolecular and intermolecular. Okay, so intramolecular referring to three different force of attractions. We have ionics, which is between ions, positive and negative ions. And then we have covalent bond, right, which is between non-metal atoms and sharing electrons. All right, so this is between non-metal atoms by sharing of electrons. And then we have metallic bond, which is between positive metal ions, all right, with delocalized electrons. Okay, so these are known as intramolecular forces. And for intermolecular forces is actually force of attractions between molecules. Okay, between molecules, for example, I have a beaker of water. So I will expect in the beaker of water, it composed of discrete molecules of H2O. Okay, we have more than one H2O molecules in it, and they are separated with a certain distance, but not as far as in the gaseous state. Why? Because they have force of attraction between molecules. And these force of attractions, we call them as intermolecular forces. Okay, and so that with these intermolecular forces, molecules can exist in a solid state, liquid state, or gaseous state. Okay, so otherwise, without all this, without all the intermolecular forces, all molecules will exist as a gaseous state, which is impossible. All right, so this is the importance of having an intermolecular forces for molecules. All right, so that's it for the intra and inter, because this is just a summary. So next, we move on to ionic bonds. Okay, now what is the ionic bonding? Like I said, it's between metal and non-metal. Example, sodium plus Cl. Okay, now sodium will have 281, 1 valence electron. Chlorine will have 287, 7 valence electrons. And what happened is these electrons from the sodium will be donated to the chlorine in order for both of them to achieve stable configurations. And therefore, sodium will form a positively charged ions, and chloride will form a negatively charged ions with extra electrons, initially 7 and 1 electrons from the sodium. So this is the dot and cross or the Lewis diagram for sodium chloride ions. And what else we need to know about ionic compounds? Ionic compounds will always with high melting point and boiling point. Okay, high melting and boiling points. All right, why? Because of the strong ionic bond, or because of the strong electrostatic forces between positive and negative ions. All right, and ionic compounds are usually soluble in water, but insoluble in organic solvent. Now, what is that? Why is that soluble in water and why is that insoluble in organic solvent? Because ionic compounds are polar because they're positive and negative charge. Water is also polar. We will talk about that later. So polar compounds were able to dissolve in water due to the polarity, but insoluble in organic solvent because most of the organic solvents are actually non-polar. Means there is no positive and negative charge. Okay, and ionic compound should be a good conductor of electricity. In the molten state or in aqueous state. Molten state means you just melt the compound without the additions of water. Aqueous state means you actually dissolve it in water so that they have free moving ions to conduct electricity. So ionic compounds are non-conductor of electricity when they're in a solid state because there is no free moving ions at all. When they're in a solid state, the ionic bonds are the strongest between ions and they are not allowed to move. All right, so this is the ionic bonding. So ionic bond or ionic compounds is always hard, all right, and brittle, all right, and high melting boiling points. So these are the basic properties of ionic bonding. or ionic compounds. All right. Next, we look at covalent molecules. For example, covalent bond. Okay. Like I mentioned just now, covalent bonding is by sharing of electrons between non-metals. Non-metal, non-metal. Okay. Sharing of electrons. And then what next is we give an example. Let's say I have CH4. Now, how the Lewis diagram looks like for CH4, because they're sharing electrons, so we only consider the valence electrons. Now, let's say I have 1 carbon and 4 hydrogen from the CH4. So, how many valence electrons for carbon? I should have 4. How many valence electrons for hydrogen? You only have 1 hydrogen. So, therefore, each hydrogen will donate out an electron to share with carbon, and carbon will take out 4 electrons to share with 4 hydrogens. And this shared pair of electrons, okay, we call it as bonding pair or a covalent bond pair. Okay, so how many bond pair here? How many covalent bond pair here? I have 1, 2, 3, 4. 4 shared pair of electrons, we call that as 4 bonding pair or 4 bonding covalent bond pair. Okay, it's up to you how you name that, as long as you know this is by sharing and this is a covalent bonding. Okay, next we look at some physical properties. It is opposite of ionic compound because it always has low melting point and boiling points. Okay, why is it low melting point and boiling point? Because for these covalent molecules, they have strong covalent bond. Okay, they have strong covalent bonds, but during melting and boiling process, they are not breaking the covalent bond. Instead, they're actually breaking the weak intermolecular forces. Okay, if you still remember what is intermolecular forces, it's the force of attractions between molecules. So we are not breaking the covalent bond here, like this CH4. We are not breaking the bond between C and H, but we are actually breaking the bond between CH4 molecules. We are breaking the attraction force here. So this attraction force is weak, is much weaker than the covalent bond or than the shared pair of electrons. Okay, therefore they have low melting and boiling points. All right, and what else? Are they a conductor of electricity? No, covalent molecules are non-conductor of electricity in whichever state, liquid, gas, or solid state. Why? Because they are in a molecular form, there is no ions, there is no free moving electrons. Of course, there are some exceptions. We'll talk about that later, but generally, covalent compounds or covalent molecules are non-conductor of electricity. Okay, and covalent molecules are usually not soluble or insoluble in water because covalent compounds are usually non-polar. This is just a general statement. Okay, we will go into detail later in the intermolecular force. All right, and they are actually soluble in organic solvent because, like I said, generally covalent compounds are non-polar. Organic solvents are also non-polar. So non-polar were able to mix with non-polar, polar mix with polar. Okay, and generally covalent molecules are soft, okay, because of the weak intermolecular forces. It's not as hot as ionic compounds. So this is covalent bonding. Okay, next we're going to look at bonding or bond pair and lone pair. Now, how to differentiate between bond pair or bonding pairs with lone pairs? For example, I have nitrogen with 3 hydrogen, ammonia gas. You see that? NH3. Okay, we draw the Lewis diagram out. So nitrogen should have 5 valence electrons. So I have 1, 2, 3, 4, 5. And each hydrogen, as usual, 1 from each. So they will be forming a shared pair of electrons with each hydrogen. So I have 3 pairs of electron here, or 3 covalent bonds here. These 3, we name them as 3 bond pair. Okay, and you can see that I have 5 valence electrons, only 3 being used up. I have 2 more electrons which is extra and involved in no bondings because there's no atoms to form bond with it. So these 2 electrons or this pair of electrons is actually something extra. So this is what we call a lone pair of electrons. Okay, this is just for you to differentiate what is bond pair and what is lone pair. So how to know whether a molecule or a compound with lone pair and how many bonding pairs? We need to draw out the Lewis diagram. Once we have the Lewis diagram, we can identify, okay, I have 3 bonding pairs, like in this case, and 1 lone pair. It is important to determine the presence of a lone pair because these will determine whether a molecule is polar or non-polar. Again, we will talk about that later. So this is bond pair and lone pairs. Okay. And next, we're going to look at the last intramolecular force, which is metallic bond. Okay, what is that metallic bonding? For example, I have a solid of sodium. Okay, I have a solid sodium. How the structure of solid sodium looks like. So sodium in nature, they will release its valence electrons, forming sodium plus because to achieve stable configurations. And let's say I have a solid of sodium stripe here, 3 sodium ions in it. So how many electrons being released out? I have 3 sodium ion means I have 3 electrons being released out. Okay, and what happened to these 3 electrons? These 3 electrons are actually free to move. So we call these 3 electrons as delocalized electrons. So they are free to move across the 3 positive ions. And where does the attraction comes from? The attraction is between the positive ions with the negative electrons, and these negative electrons will be attracted to another positive ions, and these positive ion attracted to the electrons here, and this electron attracted to the positive attracted to another electrons. So they are attracting each other between positive ions and electron. This attraction force, we call it as metallic bond. Okay, so this is metallic structure. And based on the presence of these delocalized electrons, metal or metallic structure are usually soft. Even though they have a strong metallic bond, but they are soft due to the movement of the delocalized electrons, because the movement of these delocalized electrons acting as a cushion between the positively charged ions. So you can easily bend them. You can actually, it's malleable, so you can deform them into different shape and different models. So that's why metals like copper, all these, you can draw them into wire or different shapes due to the cushions of the delocalized electrons. And of course, in terms of melting point and boiling points, even though they are soft, like I said, the attraction force is still strong between the positive ions and the electrons, so they still have high melting and boiling point. All right, so among all 3 bondings here, ionic bond, covalent bonds, and metallic bonds, they are all actually strong bond or strong force of attractions. Okay, ionic bonds will have high melting boiling point. Same goes to metallic bond, high melting and boiling points. Covalent bond is strong, but why they have low melting and boiling point generally is not due to the covalent bond, it's due to the intermolecular forces, like I mentioned just now. So this is just a reminder for you. All right, so we are done with the intra bondings. All right, sorry, let me erase that. Okay, next we move on to polarity. Okay, bond polarity. What is that bond polarity? In a simple way, when a bond is polar, they should have charges, positive and negative charge. If a bond is non-polar, then they shouldn't have any charges. So how do we know a bond is polar or non-polar? Now, the bond polarity only applicable to covalent bond. Okay, they are not applicable to metallic and ionic. Why? Because ionic and metallic apparently both are actually polar. They are just polar because they have charge. Like ions, they have positive and negative charge, and metallic, they have positive ions and negatively charged electrons. So they are only polar bonds there. Okay, so in this case, only covalent bond can be divided into 2. One is a polar bond. Okay, a polar covalent bond. Another one is a non-polar covalent bond. Okay, now how do we know whether a bond is polar or non-polar? Let's continue. We talk about polar bond first. Okay, now let's say I have an atoms of C, okay, sharing electrons with H. All right. And then I have a C sharing electrons with F. All right. So in this case, which bond do you think, both are covalent bonds, which one do you think is actually a polar bond? It's very simple. Look, now between C and H, all right, in terms of the electronegativity, is very small, which means the electronegativity between carbon and hydrogens are very minimum. So what is that electronegativity again? Electronegativity is tendency to pull electrons, which means between carbon and hydrogen, the pulling force across these shared pair of electrons are actually quite similar. So carbon will exert certain force on the pair of electrons. Hydrogen also exerts certain force on the pair of electrons, and both pulling forces are almost the same. So this pair of electrons between C and H will not move to either left or right. They will just stay in between them and evenly shared between them because the pulling force from both carbon and hydrogens are the same. So this is what we call a small difference in electronegativity. Okay, but if you look at C and F, obviously fluorine is highly electronegative, okay, or electronegativity for fluorine is high, and what happened is much higher than carbon, so these pair of electrons will actually move towards fluorine. And when these electrons are moving towards fluorine, let me draw it out. So the pair of electrons will not be in between C and F, but the pair of electrons will move closer to C and F, like that. Initially, they're evenly shared, but because fluorine are highly electronegative, so they will pull the pair of electrons towards itself. Now, what happened is the fluorine atoms here, because they have a higher share of the pair of electrons, so these will become delta negative. Delta means partially negative. All right, and what happened to the carbon? The carbon will have less share for the pair of electrons, and the carbon become delta positive, partially positive here. Now, when a covalent bond forming a positive and negative, this is what we call a polar bond. Okay, this is what we call a polar bond. And non-polar bond is the CH bond. This is a non-polar bond. Okay, so this is a non-polar bonds. So you must be able to differentiate between polar bond and non-polar bonds. I give you more example here, just in case. Let's say, for example, I have CH3, Cl, and then I have H2O molecule, and then I have HF, and then I have H2. All right. So now all of them are actually covalent molecules with covalent bond within them in a molecule. Now let's check, is this bond polar between C and H? Like I said, C and H, the electronegativity difference are very small, so the pulling force towards the electrons are almost the same. So the pair of electrons between C and H will not move to either left or right, they will stay in between them. So it's still evenly shared between carbon and hydrogen. And therefore, this is nonpolar. CH bond here, nonpolar. CH bond here, nonpolar. So there's no positive and negative. All right, but what about CCl? Cl is also another element which is highly electronegative. And what happened is they will pull the electron towards itself, and your Cl will become delta negative. Your carbon instantly become delta positive. CCl is actually forming a covalent bond, which is polar. All right, let's go for H2O. Again, we can see oxygen is highly electronegative, so they will pull electron towards itself. Oxygen is always negative, and then the hydrogen that bonded to it will become partially positive. Again, this is known as polar covalent bond. What about H and F? Same thing. F is delta negative because it's highly electronegative. This will be delta positive. Again, between HF, it's a covalent bond, which is polar. And then between H and H, what about these guys? Both are the same element, both are hydrogen gas. So what do you expect in terms of the electronegativity? Exactly the same. When they are exactly the same, the electrons, the shared pair of electrons here will not move left or right. They will stay in between them. So this bond is actually non-polar. So out of these four, 3 of them are actually with polar bonds, and between hydrogen atoms, the covalent bond here is non-polar. So this is how we decide whether a bond is polar or non-polar. All right. Next, we look at polar, and non-polar molecules. Now, just like we talk about bonding, now we talk about whether a molecule as a whole picture, is polar or non-polar. This is also very simple. Now, usually a molecule with polar covalent bonds, the molecule itself is polar. A molecule with non-polar covalent bonds, the molecule is actually non-polar, right? Again, there are some exceptions. I give you an example here. For example, I have NH3. All right, and then I have a lone pair here. All right, and then I have H2O, and then I have CH4, and then I have a nitrogen, and then with CO2. All right, and then I have SO2. Okay. Out of these 6 molecules, can you identify whether they are polar or non-polar? Now listen, before we know a molecule whether it's polar or non-polar, we need to check whether the covalent bond in the molecules are actually polar or non-polar. So if the covalent bond presents are polar, usually the molecule is polar. So for example, in this case, between N and H, is it polar? Yes, polar, same. So all 3 are polar, and then you have a lone pair here. Now listen, guys. Whenever you see a lone pair at the atoms, okay, like this, at the central, then this atom will automatically be delta negative, and the rest that attached to it will be delta positive. Now, why is it so? Same concept as just now. Why nitrogen has a lone pair? Because nitrogen is highly electronegative. This is the first reason. Second reason is because nitrogen has 5 valence and you only form 3 bonds. So 5 valence electron minus 3 bond, you only left 2 electrons, and that's why you have a lone pair. So 2 reasons why it has a lone pair: because they are highly electronegative and because they have 2 extra electrons. So whenever you see a lone pair in an atom, that usually making it a delta negative. So this whole molecule with polar bonds and also a lone pair, this molecule is actually known as a polar molecule. Okay, now what about H2O? Between O and H, which one is delta positive, which one is delta negative? Definitely O is negative, positive, and positive. And these will be a polar covalent bond for both. The whole molecule will be polar then. All right, CH4, there's no electronegative elements in it. So CH4 is obviously non-polar because there's no polar covalent bonds. Between nitrogen, of course, non-polar. Again, nitrogen, they are the same. They have the same electronegativity. They have the same pulling force towards the shared pair of electrons. All right, non-polar. And what about carbon dioxide gas? Carbon dioxide gas, yes, I have an oxygen here, which is delta negative. Oxygen on the other side, delta negative, and then your carbon will be delta positive. Now, is this a polar bond? Yes. Is this also a polar bond? Yes. So both are polar bonds. So can I say the molecule is polar? No. Why is it no? Now, listen, I know you guys, some of you are confused now. It's very simple. Look, you learned that in physics, in science. If I have electrons, if I have oxygens on both sides. Now, the oxygen is the one that pulling electrons from the carbon. So this oxygen on the right pulling to the right, this oxygen on the left pulling to the left. Now, I have the same pulling force in opposite directions. So when you have the same pulling force in opposite directions, it cancels out the pulling force. When they cancel out means they cancel out the charges as well. So the whole molecule is actually non-polar. Okay, so even though you have polar covalent bond, you must check whether a molecule will able to cancel out the charges. Now, how do we know a molecule will able to cancel out the charges? If the molecule is symmetrical. If they arrange in a symmetrical manner, then they should able to cancel out all the charges That's the reason why it is nonpolar, even though they have a polar covalent bonds in it. All right. So for SO2, what do you think about this? Now SO2 is same thing like that. Okay. Now check, guys. Sulfur should have 6 valence electrons. So I use up 1, 2, 3, 4. I still have 2 more here. Total of 6. I have a lone pair. So this is delta negative, and this is with lone pair also delta negative. Right? So which one is delta positive? It's all delta negative here. Because lone pair is delta negative. This one, oxygen, we know that is highly electronegative, so it should be delta negative here, and with 3 lone pairs as well. 2 lone pairs, sorry. Okay, so which one is delta positive? Now, it is impossible for both to be negative. So in this case, we have to check which element here, oxygen or sulfur, is more electronegative. If you check the Pauling scale, which is in your data booklet, okay, I show you another slide. This is the Pauling scale. You can see now, oxygen. Here is oxygen. I have 3.44 is a measure of the electronegativity, and then we have sulfur here, which is 2.58. Now, which one is higher? Oxygen. So oxygen will be more electronegative than sulfur, and that's the reason why sulfur will become positive, oxygen maintained as negative. All right, so this is how it looks like. So is this molecule polar or non-polar? They still cancel out the charge. Can you see that? So negative charge will be cancelled out. Okay, now if they cancel out the negative charge here, what happened to the positive? If they cancel out the charge, the positive will be disappeared, right? No more charges. But the lone pair is still there. Still remember, just like I mentioned, whenever there is a lone pair, this thing will always be polar. So SO2 will still be a polar molecule. Okay, so if you're confused about this part, no worries. I will explain it further in your tutorial again. All right, so I give you a summary for this. To check whether it's polar or non-polar for a molecule, you have this condition to follow. Okay, number 1. First thing to check whether it's polar or non-polar, check for polar covalent bond. Okay, whether they have polar covalent bond or not, check for these elements. Now, when you have this element present, F, O, N, C, R, B, R, I, when you have these 6 elements in your molecule, then the covalent bond is usually polar, except the same element present, except F and F, O and O. This is non-polar, of course, because they are the same. But if all these elements are bonded to some other atoms, for example, F bonded to C, O bonded to H, N bonded to sulfur, whatever, any other atoms other than this themselves, this bond here will always be polar. Okay, so the first thing is how to know whether a polar covalent bond. Identify 6 elements, F, O, N, C, R, B, R, I. And why these 6 elements? Because they are the most electronegative elements from your periodic table. All right, so this is easier for you. Number 2, what else do we need to check? Symmetrical. Whether a molecule is symmetry or asymmetry, it will make a big difference. Now, if it is symmetrical and it is polar bonds, then it cancels out everything. Like I said, the overall molecule is non-polar. Okay, if it is asymmetrical, then the polar bonds can't be cancelled out. The charges cannot be cancelled out. Therefore, the molecule is polar. All right, and there is one more thing. The third thing here is check whether the central atom with lone pair of electrons. If you have a central atom with lone pair of electrons, then for sure that molecule is polar. Now, what does that mean by central atom with lone pair? For example, OH2. See that? I have 2 lone pair here because initially I should have 6. 1, 2, 3, 4, 5, 6. These 2 pairs of electrons are remaining after they form bond with 2 hydrogens. So whenever you have lone pair at the central atom, then yes, this is a polar molecule. Okay. For example, H2S. Is this a polar molecule? sulfur is not from the list of FONClBri, but sulfur has lone pair. Also, same as oxygen, I have 1, 2, 3, 4, 5, 6 valence electrons. I have 2 pair of electrons left, and this sulfur is actually the central atom. Okay, so this is polar bond as well, or polar molecules as well. All right, so you need to check whether they have FONClBri. Second, you have to check whether there's a lone pair there. Third, you have to check whether they're symmetrical or asymmetrical in terms of the molecules. All right, so this is polar and non-polar bonds. All right, let's move on to the next part. Next will be the last part of this topic, which is intermolecular forces. This is quite important to identify the physical properties of most of the covalent molecules. Now, intermolecular forces divided into 3. We have hydrogen bonding. We have dipole-dipole. I'll put a square here, dipole-dipole forces. And then we have London dispersion force. Okay, now among these 3, which one is the strongest? Hydrogen bond is stronger than dipole-dipole. Dipole-dipole is stronger than London dispersion force. Okay, now how to categorize them? First thing first, London dispersion force is everywhere, which means whenever 2 molecules come into contact with each other, they will always form London dispersion force. This is the basic intermolecular force exists between molecules. And in addition to the London dispersion force, some molecules will give you a dipole-dipole forces. This is an additional intermolecular forces which makes the force of attractions between molecules stronger. Or some molecules were actually forming hydrogen bonds. Now, how do we know a molecule given is actually forming dipole-dipole, hydrogen bond, or just purely London dispersion force? All right, so it's very simple. Look, if you have non-polar molecule, okay, if you have non-polar molecules, then only London dispersion force exists between molecules. Only this intermolecular force exists between them. If you have non-polar molecule, that's it. No other intermolecular forces when your molecule is actually non-polar. All right, but if you have polar molecules, okay, when you're polar molecules, then it could be hydrogen bond, it could be dipole-dipole forces in addition to London dispersion force. Okay, so non-polar molecules, only one, which is London dispersion, that's it. For polar molecules, it can be hydrogen bond, it can be dipole-dipole. And how do we know a polar molecules are forming hydrogen bonds or a dipole-dipole? Let's continue. Let's say I have 2 molecules, A and B, because it's intermolecular forces, so it must be between molecules. Now, in order to form hydrogen bond, one of the molecules can be A or B. I'm just using one of it. One of the molecules must have a hydrogen atom, which is delta positive, partially positive. Now, how to have a hydrogen atom which is delta positive? This hydrogen must have attached to a electronegative element. Make sense? If they are attached to an electronegative element, the electrons will be pulled towards that, and your hydrogen will have less share on the pair of electrons, which is the covalent bond, and therefore making it a delta positive. All right, so another molecules must have either F, O, or N, either one of them. And these 3 are highly electronegative, so they must be delta negative then. So either one of these, FON with a H from 2 different molecules, the force of attractions formed between them, they call it as hydrogen bonding. See that? So basically, if you have 2 molecules, or if you have a compound, if I give you molecules and I ask whether they're forming hydrogen bond or not, then what are you going to check? Between molecules, one of them must have hydrogen, which is delta positive. One of them must have F, O, or N, which is delta negative. This is always true. And when these 2 come together, you are forming hydrogen bond. All right, so this is for hydrogen bond. And what about dipole-dipole? Dipole-dipole is any other polar molecules, which means not between H and FON. The rest of it are actually forming dipole-dipole. For example, I must have a molecule of A and B here again. And what do I have here for molecule A? I must have an atom, which is delta positive. For example, carbon. It can be any non-metals which is delta positive. All right, any non-metal which is delta positive. It can be silicon. It can be, yeah, basically I think that's it. Nothing much, which they are non-metal and they must be delta positive. And another molecule must have FONClBri. All right. So what happened between FON? There are always 6 of them. They're always negative. And then when they're forming attraction force between the positive and negative, this is what we call a dipole-dipole. Now, if you realize this, hydrogen plus is not involved here. Now, why do I exclude hydrogen plus? Because if hydrogen delta plus were to be in one of the molecules, it still can form dipole-dipole, but this hydrogen is only meant for Cl, Br, and I, not for FON. If hydrogen plus with FON, then it will be hydrogen bond, not dipole-dipole. You get what I mean? So as long as between hydrogen plus with FON, they are forming hydrogen bond, other than that, they are forming dipole-dipole, if the molecule is polar. All right, so I try to give you a summary here again, example. So let's say I have H2O, all right, first example. Second example, pH3. And then third example, I have CH4. And then fourth example, I have CH3Cl. All right, now try to identify what type of intermolecular force form between water molecules. Means I have 2 or 3 water molecules now together, and what force of attraction is formed between them. For H2O, can you see that? Let's say I have 2 molecules of H2O. What do you see from here? Do I have a H delta positive between O and H? Yes, the H is delta positive. And do I have FON? Yes, this is delta negative, delta positive, delta negative. You see that? Between H positive and O negative. So the force of attractions between them, we call that as hydrogen bond. That's right. Okay, so water, they are forming hydrogen bond. What about pH3? pH3 arranged like that. You have P and H. So P should have 5 valence electrons. Take out 3. I still have a pair left. Like I said, P is a central. You see that? They are at the center. Central atom means the one with the lower number in the molecule. So pH3, between P and H, which one with the lower number? Of course, the P. So this is a central. And the central atom is actually with a lone pair. So the central atom is negative. This is positive then. Okay, the H is positive. And imagine I have another pH3 around here. So what's force of attractions between them? This is still positive. The central atom is still negative. So a positive hydrogen with a positive P. Can I say this is a hydrogen bond? No. Why not? Because hydrogen plus with P, not FON. Not FON. That's the reason why for pH3, they are forming dipole-dipole. Okay, for pH3 between molecules, they're forming dipole-dipole. They're still attracted to each other, but they don't call it as hydrogen bond. They call it as dipole-dipole. What about CH4? CH4 itself is non-polar, guys. Because the molecule is actually non-polar, so only London dispersion force. See that? And CH3Cl, what do you think? CH3Cl, is it a polar molecule? Let's draw it out. Yes, delta negative for Cl, FON, Cl, Bri. Cl is here, so the carbon attached to it is delta positive. This is one molecule. Okay, imagine I have another CH3Cl here. Delta negative on the Cl, delta positive on the carbon. And what happened? I have positive attracted to negative. I have positive here attracted to another negative. So they are attracted to each other and they are polar. What do we call these as? Dipole-dipole. So CH3Cl forming dipole-dipole. Not hydrogen bond again, guys, because there isn't any hydrogen with delta positive. Now you may ask these questions. Why? Because in the structure I have hydrogen. See that? I have a lot of hydrogen. Why not? This hydrogen is delta positive. Because the hydrogen here isn't attached to an electronegative element. They are attaching to a C, not the Cl. So the pooling of the Cl will just happen between C and Cl. It will not happen between C and H. So therefore your H will remain as neutral. There's no positive charge. And therefore there is no hydrogen bond formed. So this is dipole-dipole for CH3Cl. All right, I will give more example in the tutorial. Hopefully this can help part of it when you attempt your question again. All right, so let's move on to the last part where we need to check the solubility. Okay, this will be the last one. Okay, we need to check whether two compounds together they are soluble, they are miscible. All right, first thing first, I have a beaker of water, H2O. All right. So again, I expect a lot of water molecules here because they exist as discrete molecules. And what happened next? Let's say I have a CH4 here. I always use that because it's nonpolar anyway. And then let's say I have an ammonia here. Let's say I have HCl here. Let's say I have HF here. Now, can you tell me which one is actually miscible with H2O? Miscible means they can dissolve and mix with it evenly, which means you will not see two layers form. When you mix them, they mix thoroughly together. Okay, it's not like when you mix water with oil. Okay, you can see two layers. In this case, I'm mixing these four one by one, of course. And can you tell me which one is actually miscible or actually can dissolve in water? One by one, we know that water is actually polar. Okay, next, water molecules forming hydrogen bonds between molecules. Okay, in order to mix with water, the molecule here must be polar. Next, the molecule that mixed with it must have hydrogen bond, or they must able to form hydrogen bond with it. All right, now let's check. Is CH4 polar? And so out. Is NH3 polar? Yes, first is a yes. Then we have to check. Is NH3 able to form hydrogen bond with water? I have H plus, N minus. I have H plus, O minus. So number 2 is a yes. So both yes. So yes, it can be soluble in water. What about HCl? Is it polar? Number 1, yes. Number 2, can they form hydrogen bond with water molecule? I have H plus here, delta positive. All right, I have O minus here. So it's a yes as well. So it's a yes. So it can form, or it can be soluble in water. What about HF? Delta negative, delta positive. I have O negative, I have H positive. Yes. So first, is it polar? Yes. Number 2, can they form hydrogen bond with water? Yes. So these 3 will be able to form hydrogen bond with water, means these 3 were able to dissolve in water. So out of the 4, only 1 insoluble, which is CH4. All right, so this is how we determine whether a compound given is soluble in water or not. You see that? So you always check that. So in order to make sure you know what's going on between them. I guess that's it for your chemical bonding because it's just a summary. If you have more things to ask, please feel free to raise it up during your tutorial sessions because we need to have more discussion, more examples given so that you can understand it well. All right, so that's it for this summary video. I'll see you in another video, which is your tutorial 2. All right, see you.